Crystalline polymers, polymers like polyethylene, which when we encounter it, it actually has quite a high degree of crystallinity. And we talked about some of the questions that it was important to have answers to when we were thinking about semi-crystalline polymers. We asked questions like, how do we find out about the crystalline structure at the level of a unit cell, in the same way as you would with a small molecule crystal. And of course you can do that with X-ray diffraction, but we saw it's not quite as simple as with a small molecule because you very rarely get single crystals. You have a polycrystalline material, which gives rings like a powder pattern. If you pull on a fibre, you can break those rings up into layer lines. But then later we said you can get single crystals. They're very, very small, they're lamellar, and they're really interesting because although they're very thin plate-like crystals, the chains go across the crystal and fall backwards and forwards. And we're going to meet that idea again today. Today we're going to talk more about the morphology of a semi-crystalline polymer. In other words, how those crystalline regions are actually organised in a lump of something like polyethylene. And then we will move on to talk about one technique which can be used to detect the sorts of transitions we've been talking about, the transitions involved with crystallinity, like the melting transition, and also the transitions we talked about earlier, where we convert between a glassy material and a rubbery material. And then finally today, I'll mention a little bit of research that's going on in Manchester, which asks the question about what happens if you make a polymer that can't rearrange like this. So let's start by thinking a bit more about semi-crystalline polymers, and in particular their morphology. Now, what sort of techniques are available to us to actually work out what's going on inside a lump of polyethylene or a polymer like that which can crystallize? And we can start out with microscopy, and I'm going to mention a little bit about what we can learn from optical microscopy and electron microscopy. Another technique which is actually important, but I'm not going to mention it, is small angle X-ray scattering, which is using X-rays but looking at much smaller angles than we normally do to get information about larger spacing. Spacing's not about what's within a unit cell, but spacing's actually about the sizes of the crystalline regions. But I'm not going to talk about that with you, but if you go on and do research in this area, you might need to know about that technique. But we are going to say just a little bit about microscopy, starting with optical microscopy. So this is a good old-fashioned microscope that uses ordinary visible light. And of course, optical microscopy is limited, its resolution is limited by the wavelength of the light that we're using. So you can't see very, very small things, just moderately small things. But we can see some quite interesting things if we look at a sample of polyethylene under an optical microscope, because we realise there's a structure there that's actually big enough in many cases to be seen. And what we see are little spherical structures which actually tend to run into each other, as we'll see in a bit, which have some sort of substructure, sort of fibrous aggregates. And these things are called spherulites. They can be up to 1 millimetre in diameter, usually smaller than that. And so, just with an optical microscope, we can learn that what we have in a polymer like this is actually, we've got structure on quite a large scale. So we said that the crystalline regions were very, very small, but they're actually organised in some way into larger structures. And what we're going to ask about is what are those structures. Now, just looking at something with a microscope tells you a certain amount, but there's a trick that people quite often play when they're looking at ordered materials by optical microscopy, and that is to put your sample between what are known as crossed polars. Now, you should all have some idea of what light is. It's electromagnetic radiation. You know that we can treat it classically, we can treat it quantum mechanically, but in the simplest case, classically, what we have is electric field, magnetic field, perpendicular to each other. And in ordinary light, we've got waves vibrating in all directions, and you should all know that we can find something, a material which will actually select out light vibrating in just one plane. Many of you probably have sunglasses which are polarized, that's what they do. And so we have a piece of Polaroid film, shine some ordinary white light on it. What comes through is more or less plain polarized. And if we have another, piece of Polaroid film or another polarizer which is oriented the same way as the first, then we can see right through it. In the good old days when we had old-fashioned overhead projectors, I could demonstrate this very clearly. It's perhaps not quite so easy to see here, but more or less, can you see through that a little more or less?
Yeah.
Now, if I turn one of those through 90 degrees, because light that gets through the first one, gets through the second. If I turn one through 90 degrees, light will no longer get through. It's now completely black, yeah? Light gets through, light doesn't get through. Light gets through, light doesn't get through, yeah? Can we see? Is there enough light in here to see? The people at the front, at least, can tell, yeah? People at the back, you should be at the front and you could see what was going on. Okay. Now if we put something between those polarizers, if it's isotropic, that means it's optically the same in all directions, then no light comes through. But if we put something between those Polaroid films which is birefringent, that means it has different refractive indices in different directions, and therefore twists the plane of plane polarized light. Some of you probably know something about that from what you've learned about chiral things, twisting light. Yeah, some people are nodding, so someone knows what I'm talking about. Then you start to see colours and things. And so one way of seeing if you've got order in a sample is to look at it between cross polars. Because if there's some organisation and you have different refractive indices in different directions, then instead of nothing, you'll start to see different colours. And the patterns that you see actually can tell you something about the structure that you've got. Now, some people arriving. Make sure you have you got a handout? Plenty of handouts here. You know, I'm coming to leave. And still we come. There's some handouts here. There's some seats here. Perhaps some people on the edges might like to move in so that people can find their way. Now if we look at a sample of something like polyethylene, through an optical microscope between crossed polars, we actually see a pattern. Because of course we've got organisation of the molecules. That's telling us something about the way those crystalline regions are organised. And it's a very distinctive pattern. Our spherulite actually has this, what's called a Maltese cross pattern when seen through an optical microscope between cross polars. And if the spherulites all run into each other, then you see lots of Maltese crosses all joined together. Now let's just see if we can see an example of this. Okay, now this isn't actually polyethylene, it's polyethylene oxide, because the polyethylene oxide crystallizes, you can get it at around room temperature. So it's a nice polymer to actually study what happens as it crystallizes. So what we're going to see is what happens when you have a sample which is originally effectively a liquid or fluid, and or even an amorphous solid, rubbery solid, and it's going to crystallize as we watch it. And this is an image from optical microscopy between cross polars. So here's our spherulites. You can see the Maltese cross pattern and you can see them growing, and if you let them grow long enough they'll eventually all grow so they merge into each other. see new little nuclei starting, and then this is a nucleation growth process. There'll be something somewhere, which is the point at which nucleation can occur, and then the spherulite will grow outwards from that point. So that's the sort of thing one sees, visibly. We've got these structures, and between cross-polars they have this very distinctive pattern, and very many different polymers show the same pattern, the same sort of behavior. Polyethylene, polyoxyethylene, and many other polymers all show this sort of spherulitic structure and Maltese cross type pattern. So one can ask ourselves, what is that actually telling us? What does that particular pattern mean? And what you do is you go off and you talk to some physicists who work all of these things out, and they'll tell you that you're going to get this pattern if the refractive index perpendicular to the radius, so if this is our radius, and the refractive index perpendicular to the radius at any point around this spherulite is larger than the refractive index parallel to it. In other words, the refractive index going along a radius is smaller than the refractive index going around any circle within this spherulite. So there's some information. And actually, if you work it out, again, people go away and they model these things. If you think about, for example, a single polyethylene chain, then the refractive index parallel to the chain, that's actually along the chain, is larger than the refractive index across the chain. So this then tells us that, on average at least, those chains are aligned perpendicular to the radius of a spherulite. So although this is optical microscopy, we can't see anything as small as a molecule or even the little crystallites that are involved with an optical microscope, we can nevertheless infer something about how the molecules are, on average, organised within that spherulite. But to get more information, we want to look more closely. So then we would go to another technique. So if we want to resolve things which are too small to be seen in an optical microscope, we go to something which has a smaller effective wavelength. We move to electrons. We use an electron microscope. Now if we study a typical polymer sample in an electron microscope, we can see more detail. We said we can tell from an optical microscope we have these spherulites, these sort of more or less spherical structures which have some sort of structure, fibre-like structure inside it. And if we look very closely, we realise that what looks like fibres are actually made up of little platelets all stacked together. Lamella, a lamella structure is a very thin plate-like structure. Remember, yesterday we said when we make single crystals of polymers, that's the sort of structure we get. So we have, in our bulk polymers, something like lots of those little single crystals all stacked together. Now, what we know from single crystal studies, as we mentioned yesterday, is that when you have one of these lamellae, the chains go across the lamellae and fold at the surface. So we can infer that in the bulk, where we can see lamellae, we have a similar arrangement. Although, of course, because they're all stacked up, one chain might fold one time, another time it might move into another lamellae, so we may get connections between the lamellae. But we have something like a more or less chain-folded structure within the lamellae, which are in the fibrils, which are within the spherulites. So now we can start to build up a picture of how things are organised. We have these big structures. We call them spherulites. And on an optical microscope, between cross-polars, they have that distinctive Maltese cross pattern. Within the spherulite, we have some sort of fibrous structure, which itself is made up, well, in fact, if we look closely, they branch. We've got non-crystalline material. Remember, we said that we're never dealing with a completely crystalline sample. There's non-crystalline material there as well, amorphous material, which will be either glassy or rubbery, depending on the temperature. And there'll be amorphous material between the little sort of branches, between these little fibrils. But the fibrils themselves are made up of stacked lamellae. So you've got little crystalline lamellae, and actually little amorphous bits between the lamellae. And if we think about if the lamellae are more or less parallel to the the fibrous type structures that we can see, and the polymer chains are going across the lamellae, then we end up with a situation where the polymer chains, on average, more or less, are perpendicular to the radius of the spherulite, which is what we inferred from the optical microscopy. So we have quite an interesting polyethylene, simple polymer, just a long chain hydrocarbon, but actually you have quite a complex structure in there, with these little molecules folding backwards and forwards. Remember, at the local scale, it's a planar zigzag, and they pack orthorhombically, coordination number of 6 within the unit cell. But when they get to the end of the lamellae, they will fold over or go into another lamellae, and we've got little disordered regions around those lamellae. But those lamellae are stacked together in little fibrils which move out from a point of nucleation when the thing crystallizes, so we end up with these large-scale structures that we call spherulites. So now you know a certain amount, just a little bit, about the sorts of interesting questions that there are about semi-crystalline polymers. There's another question that we haven't particularly talked about, which is, how do you know how crystalline something is? If we've always got some crystalline material and some amorphous material, a key question is, there a lot of crystalline material or only a little bit? One technique that you can use, although I'm not going to actually talk about it, one technique that you can use to determine that is actually the technique we are going to mention. We're not going to focus on that aspect of it, which is differential scanning calorimetry. You can also use X-ray scattering if you can calibrate things effectively, because the ratio of the broad diffuse halo that you get to the sharper peaks that you see is telling you about how much crystallinity you've got in the sample. But what I'm going to do for the next bit of this lecture is talk about a technique which is quite useful to us. It's one technique for getting information about some of the things I've been talking about. Remember, we started talking about the different physical states which we might encounter polymers. And we said, in particular, we mentioned that we might meet them as rubbery, elastomeric materials. We talked a bit about that. We might meet them as amorphous, glassy materials, and we might meet them as fairly as tough but moderately flexible semi-crystalline materials. And then we talked about the way in which you can get from a glass to a rubber if you just raise the temperature, or from a rubber to a glass by lowering the temperature. And then we said that some polymers, if they have regular enough molecular structures, can also crystallize. And we talked about the glass transition, which is rather an odd transition because it depends on kinetics. It's not a first-order thermodynamic transition. And we talked about the melting point, which is a first-order thermodynamic transition, but it's still not as well defined as for a small molecule, partly because those little lamellae that we talked about, they can have different thicknesses. Depending on the rate of crystallization, the temperature of crystallization, you actually get different lamellar thicknesses. That's actually where small angle X-ray scattering comes into play, because that tells you about the distances between the lamellae. But we're not going to talk about that here. Well, I was going to say, how do you actually work out where the glass transition is, where the melting point is for one of these things? There are a number of techniques. We mentioned one. You could use dilatometry. You can follow volume changes. Remember little plots of volume? That's a good old-fashioned technique. But nowadays you're more likely to use something which enables you to follow thermal changes or mechanical changes. And we're going to talk about a technique which follows thermal changes. If you remember, when we were talking about the glass transition, we said when we have a first order thermodynamic transition, you get a step change in something like volume or enthalpy. When you have a second order thermodynamic transition, you get a change in the temperature dependence of those quantities, but no step change at the transition. And the glass transition is more like that. If you follow volume, it doesn't do that, it just changes its slope as you increase the temperature. And similarly with enthalpy. Now, a derivative of enthalpy with respect to temperature is heat capacity. So we monitor heat capacity, directly or indirectly. It's a function of temperature. We have a way of monitoring transitions and working out what sorts of transitions they are. So you've all met calorimeters of one sort or another. Probably most of you in a teaching lab have done an experiment with some sort of a calorimeter, yeah? So calorimeters, there are lots of different kinds of calorimeters. They're all about measuring heat changes. This is a scanning calorimeter, which means that we're actually going to see what happens as we change something, as we scan, in fact, over temperature. So this is a type of experiment where we're going to actually change the temperature of something and monitor what's going on. And it's differential because we're going to compare what we're looking at to some sort of a reference. So what do we have? Now actually there are a number of different kinds of DSC, or differential scanning calorimeters. Different manufacturers actually make instruments which operate in slightly different ways. And I'm just going to show you one way in which it's done. Okay? And we'll see a bit later why it's important that you need to be aware that actually different instruments may function differently. Because as always, as good scientists, if you go away and you do an experiment, you as the researcher needs to understand the instrument that you're using. Don't rely on technicians. Don't rely on what the computer prints out. You're the person who has to know what's going on, understand what's going on, and interpret the results. And you can go away and get someone to give you some DSC data, but the results will look different depending on how the instrument works. So you always need to know what it is that the instrument you're using is actually doing. So I'm just going to show you about one method that you need to be aware that there are other methods. So in the method I'm going to talk about, you have two little pans. You put your sample in a little pan. Might be aluminium, it might be something tougher, depending on what temperature you're going up to. And that sits in the machine on top of a little heater. And there's also a temperature sensor associated with each pan. And you've got to have two of them. This is comparative. You'll put your sample in one pan, and usually you'll actually just leave the other pan empty. Sometimes you'll have something else as a reference, but most commonly you'll just leave the other one empty. But that's your reference. Okay? So you've got two small pans, each with its own heater. One contains the sample, the other is usually left empty. Okay, the instrument then, according to a program that you set, heats both pans at a specific rate. Often it's, say, 10 degrees centigrade per minute. Bear in mind that we've said that one thing we want to look at is glass transitions. Glass transitions depend on the rate at which you do something. Change the heating rate, you will actually change the temperature at which you see the transition. So it's important to know and to be aware that heating rate actually has an effect. And experiments are often done quite fast, but sometimes you might want to slow them down. Now, what's going to happen? To keep both pans heating, if you've got a sample in one pan, that's extra heat capacity, so you need to put more heat into that to keep it heating at the same rate, depending on the heat capacity. And what we're going to do is to just monitor the difference in the heat output of the two heat signals. How much energy do you have to put in to keep the sample and the reference heating at the same rate? There are other variants on the theme which, for example, plot a temperature difference or do things slightly different, but this is one way of doing it, which is used by certain instruments. Okay, so what you actually plot is heat flow, how much heat are you putting out. If you calibrate it, you can convert that to a heat capacity. Often that's not actually done, but you can if you want to. But if we've got a heat capacity, then we can once it's calibrated, remember heat capacity is a derivative of entropy, so the integral, the area under the heat capacity curve, is an entropy change. So we have a way of getting enthalpy information. So what we're going to see, for example, first of all, let's imagine that we're going to go from a glassy state to a rubbery state. So we start out with a bit of a glassy polymer as our sample. We're going to heat it up. It will have a certain heat capacity. And that will change a little bit with temperature, but it'll be a fairly steady change. Now, what happens at the glass transition? Remember, there's no step change in enthalpy, but if you have something where the slope is changing, you take the derivative of that, we do get a step change in the heat capacity. So, because heat capacity is related to heat flow, if we monitor heat flow as a function of temperature, when we get to the glass transition, there's going to be an inflection. So we'll see the glass transition as an inflection in that curve. Now, I said that where that occurs will depend on the heating rate, and also you can have other things occur, which means sometimes you get a little peak associated with that, which is a purely kinetic effect. But you can take account of that by slowing down the heating rate and seeing what happens. Now, supposing we actually have a polymer which can crystallize. And let's say that we start out with it in an amorphous state. So let's say that it's not crystalline when we start out the experiment. What we're going to see, of course, is going to depend on whether it's already crystalline or not. Let's say it's not crystalline when we start out, then at some temperature it's going to crystallize. Remember, we said yesterday that the rate of crystallization was normally maximum about halfway between the glass transition and the melting temperature. So when you get to that sort of temperature, it'll crystallize. Now, crystallization, of course, is an exothermic process, and that will appear in our heat capacity or heat flow curve as a peak. And the way I've described this, it will be a peak that goes down. And then a little while later, at some higher temperature, we're going to get to the point where those crystals melt, and melting is an endothermic process, so it will appear as a peak in the opposite direction. So we can immediately distinguish glass transition, crystallization, melting, because glass transition will be an inflection, crystallization will be a peak in one direction, melting will be a peak in the opposite direction. But what you have to do is take careful note of which direction you're looking at. The way I've described it, something up is endothermic, something down is exothermic, but I said that different instrument manufacturers design their instruments in slightly different ways. You will also find, if you go to the literature, that there are DSC instruments which present the data the other way up, so that exothermic is up and endothermic is down. And so you get really confused if you don't know which instrument is being used and which way is exo and endo. So if you end up doing a project and you do this, you will always, because you're good researchers, make sure you note very carefully, is endo up or is endo down? And you will probably go to books and realise that some people aren't as careful as you are, and then you're going to get really confused. But you're going to be really good scientists. You make sure you know what you're doing, and you write down carefully, and when you plot data, you make clear what it is exactly you're doing. Now so having got those basic ideas, as I said, there are other things you can do with DSC. You can actually use DSC to get information about the extent of the degree of crystallinity, but we're just going to focus on its use for transitions. What we've said is that we can distinguish between a glass transition, a crystallization peak, and a melting peak. Let's ask about what we might expect. We're going to think about a polymer which can crystallize, but of course, as we've already said that we're dealing with a semi-crystalline polymer. There are also amorphous regions. The amorphous regions can be glassy or rubbery. And we're going to think about two different experiments with the same polymer. Okay. So, in the first case, we're going to start out with our polymer in the melt. That means we're going to start out with our polymer at a temperature above the melting point. So it's fluid or rubbery, and it's amorphous. And what we're going to do is we're going to quench it rapidly. That means we're going to cool it very, very rapidly down to a temperature below the glass transition temperature. Now, crystallization takes time. So if we can cool rapidly enough, it won't have a chance to crystallize while it's cooling. And so you'll end up, if you quench it, if you cool it very rapidly, you'll end up with a sample of a polymer which can crystallize, but it's currently glassy and amorphous. Then we're going to do our DSC experiment where I heat up and monitor what's happening. In the second case, instead of quenching from the melt to some temperature below TG, we're going to let it cool very, very slowly down to the same temperature. Now remember, early on I said when I was dealing with polymers, particularly semi-crystalline polymers, thermal history is important. This is what we mean. What has happened to that sample before you actually look at it? Now if we let it cool very slowly, we start out the same temperature, we end up at the same temperature. But if it cools slowly, it has a chance to crystallize while it's cooling. It's going to cool down and get to the temperature at which crystallization occurs rapidly. So then when you get to the bottom temperature, it's already semi-crystalline. So whether you quench or whether you cool slowly will determine whether you start out with a sample that's already crystalline or not. Thermal history matters. So let's think about what we're going to see in each case. Now if we quench the sample, it's crystalline when we start out the experiment. Now we're going to heat up in our differential scanning calorimeter. And at some point we're going to reach the glass transition. We know the glass transition appears as an inflection. So we're going to see an inflection associated with the glass transition. Remember, it's all amorphous because we quenched it from the melt. It hasn't had a chance to crystallize. It will crystallize at some higher temperature where we've got mobility. Actually somewhere between TG and TN. So as the mobility improves as we continue to go up in temperature, we'll get to a point where we'll see crystallization, which remember is an exothermic peak, which in this case is going down, but you might go to a lab with a different instrument where it goes up. So beware. Okay, so now it's crystallizing in the machine as the experiment. But we keep heating up until we get to the temperature which is going to melt. So now we're going to see an endothermic peak, a peak in the opposite direction. So if we do the experiment that way, we start out with a melt, we quench it so it doesn't have a chance to crystallize during cooling, we then heat and follow what happens. We're going to see the TG, we're going to see TC, the crystallization temperature, we're going to see TM, the melting temperature. But now let's say we started out with the same polymer sample, the same high temperature, cooled it slowly to the same low temperature, and then did the experiment. What are we going to see now? Okay, now, it will have crystallized while it's cooling. And we'll assume that it's crystallized pretty thoroughly, but remember these are semi-crystalline polymers, we never get 100% crystallinity. Most polymers are only up to 20-30%. Polyethylene might be much higher, more crystalline, but there's always some amorphous material. And so we'll still see a TG, but it'll be a smaller response because only part of the polymer now is glassy. Okay. And if we're cooled really slowly, then it will have crystallized pretty much as it can. So we're not going to see a crystallization peak, or if we do, it'll only be a small one. But we are going to see a melting peak, and possibly that'll be much bigger because we've given it plenty of time to crystallize, whereas in the previous experiment it only had a little bit of time to crystallize because we were heating quite fast. So what does this tell us? It illustrates what I said right near the start. When you're thinking about polymers, the history of the sample matters. Whether we see these transitions will depend on the sample, which will depend on what's happened to it before we do the experiment. So you need to think carefully with any sample, what has happened to it, how can we treat it to get to a certain state? So you might well, a typical example might be that you would heat it up to a melt, quench it, and then see what happens, because then you can see the crystallization temperature, then maybe do a slow cool and repeat the experiment to see what's going on there. So that's one useful technique. There's a DSC up on the 4th floor in the same lab that has all the analytical equipment. Useful technique, not the only technique, but one technique for getting information about glass conditions, crystalline inflation temperatures, melting temperatures, and other things. So what I'm going to do with the last little bit of today's lecture is talk about something that is more interesting to me. Because this is a bit of research that's taken place and is taking place here in Manchester. Because what we're talking about is a situation where we can get transitions between a glassy state and a rubbery state, and potentially, if we've got enough regularity, we can crystallize. But all of this is about how polymer chains can move around. Remember, a rubbery material, it is rubbery because the actual chains can stretch out and then recover a more favourable and entropically favourable conformation. And the glass transition is all about mobility. And if something's going to crystallise, it has to be able to reorganise itself and pack into some kind of crystalline structure. So let's ask a very, very basic question. This is an intellectual question, but it's an intellectual question which leads to some practical and interesting results. Suppose we design a polymer. We're chemists. Suppose we design a polymer that cannot rearrange in the same way. See, what nearly all the polymers we've talked about have in common is that in the backbone they have single bonds between carbons, or sometimes silicons and oxygens. They have single bonds about which rotation can occur. We talked about that, didn't we, about the rotational isomers and the different energies and such. But what happens if you design a polymer which does not have any single bonds in the backbone about which rotation can occur? We deliberately give our polymer a much more rigid macromolecular backbone. What happens then? And can we make use of that? And this is an idea behind some polymers which were invented here in Manchester, which we refer to as polymers of intrinsic microporosity, or PIMs. So the basic idea is very simple. Most polymer chains are flexible, they can wiggle around, they can rearrange, they can change conformation. If they really apply stress, they can stretch out and they can try and recover their original dimensions. They can organize themselves, if they're regular enough, into a crystalline lattice. But what happens if we remove the ability of a polymer chain to change conformation through backbone rotations? We're not going to get rid of all mobility. Every molecule at any finite temperature has got energy and it's going to do something with that energy. But we're taking out certain types of mobility. Now, so, what might we expect, just intuitively? Now, so if we've got a flexible chain, it can reorganize, it can rearrange. We can imagine it's a bit like a load of snakes that can sort of wiggle around, more or less fill space, but not perhaps wonderfully. They tend to be, Now, if we make a rigid polymer, which is also very stretched out, actually, you normally end up with a polymer which is often highly crystalline, certainly packs very efficiently, it's very dense. Usually you can't melt it, you can't do much with it, it's pretty difficult to do anything with it. But an idea we've been working on is what happens if you make it rigid, but also make it twist backwards and forwards, so that it looks like the sort of coil that a normal polymer will adopt, but it's a coil that can't actually reorganize. That the shape you get is fixed at polymerization. It can't rotate around backbone bonds and change its shape. And then we have an interesting thing, because we now have something which actually can't pack very effectively. It has a lot of extra, what we call free volume. Free volume is the space not occupied by molecules. One way of understanding the glass transition temperatures in terms of free volume, there's a theory which says that the glass transition occurs at a critical fractional free volume. In other words, as you raise temperature, things wobble around a bit more, things expand, and when you hit a critical amount of fraction of space for things to move, you've now got enough space for large-scale motions and things to become rubbery. But here we can actually trap a lot more free volume in a polymer that cannot become rubbery in the same way. Now, how do we actually do this from a chemical point of view? First of all, we want a polymer without any single bonds in the backbone that rotation can occur. And so when we're doing that, it's making what we call a ladder polymer. A ladder polymer is made up of rings all joined together. So here's the structure, and if you look at this bit of the structure, it's like a little ladder. If you're a tiny little molecular-sized person, you could climb up the rungs of the ladder. And now you've got something, you can twist it and bend it, but you can't completely rotate without breaking a bond in the backbone. But we don't want just a ladder. Ladder polymers, people have made them, they're very difficult to do anything with. We add something else, something to make it also twist and turn, what we call a cytocontortion. It's not quite like this, because actually the structure I've drawn there was a little too flexible, but similar to that. Now, how do we actually do that in terms of chemistry? Well, we can make, one way of making a ladder polymer, if you take a catechol and an activated aromatic dihalide, you can do a double aromatic nucleophilic substitution reaction, which actually is very, very efficient. To make a polymer, you need a very efficient reaction. Later, when you learn more about polymer synthesis, you'll learn that, if you don't know it already, if you're doing a step growth polymerization, where you're using individual reactions to try and make a polymer, you need 100% conversion, or you will not get a high molecular weight polymer. You need a very efficient reaction. Imagine if you were in the organic chemistry lab and you were told that it was a failure unless you got 100% yield every time. But that's essentially what you have to do to make a high molecular weight polymer by step polymerization. So you need a really efficient reaction. This is a remarkably efficient reaction if you have a suitably activated fluoromonomer. And you build a dibenzodioxane type bridge, which is actually what we have here. These are these nitrile groups which activate the fluoromonomer. We started out with hydroxyls here and here. We formed two ether linkages between aromatic rings. And to put the bend, we use very often a spirocenter. A spirocenter is a tetrahedral carbon atom that is part of two rings. We use 5-membered rings. If it's 6-membered rings, it's actually a bit too floppy. So here we have a spirocenter. And what that does is it takes one bit of ladder and it makes the next bit of ladder go off in a different direction. If you've got loads of those making up a polymer, we end up with a twisted, bent, contorted polymer chain, but we haven't got any single bonds anywhere about which we can get free rotation. So this was the first, well, we actually started making networks. This was something done by a colleague, Neil McKeown, who's now at Cardiff University, and myself, a few years back. This is one which has become particularly important, which is actually the structure that we've got here. We refer to it as PIM1. PIM stands for polymer intrinsic microporosity. I'll explain in a moment why we call it that. And we start out with two things which actually you can buy from lab suppliers. One is a bis catechol, which has a spirocenter in it, and the other is a suitably activated monomer. You can use the chloromonomer. It's easy with the fluoromonomer. If we can push this reaction, get the conditions right, we end up with this polymer that we call PIM1. Why is that interesting? It's a soluble polymer. So it's a powder, you can dissolve it in things like chloroform, tetrahydrofuran, and that means you can process it. You can make films or membranes out of it. You can make coatings and such like. But why is it particularly interesting? I said when we take out the ability, the flexibility, but put in this sort of twisting, we have a structure which can't easily pack down. These are results of computer simulations, where in a computer they try to pack these chains together, then they slice through the box of their simulation. And you can see that we've got lots of little bits of space between the molecules. Okay? And those bits of space are actually the sorts of sizes of small molecules. Little gas molecules, small organic molecules can get in there. So it actually behaves like a molecular sieve. Okay? Now, molecular sieves are also referred to, according to one definition, as microporous materials, where a microporous material is something which has molecule-sized holes, less than 2 nanometers in dimensions. So we have a processable polymer which behaves like a molecular sieve, behaves in the same way as, from many points of view, as, for example, a zeolite. And the classic experiment for showing molecular sieve behavior is to study how nitrogen is absorbed at liquid nitrogen temperature. Because nitrogen will, or a gas like that will actually absorb most strongly into the smallest gaps, the smallest holes, as long as they're big enough for nitrogen molecules to get in. And that's because, nitrogen, if you think about it, you know about intermolecular forces, it interacts weakly with surfaces. We've got a surface there and in a weak interaction, and put another surface very close, then the intermolecular potentials are reinforced between those two surfaces. So you get a stronger absorption between two surfaces that are very close together than between a single surface or two surfaces that are a long way apart. So if you study, starting at very low pressure, increasing the pressure at liquid nitrogen temperature, how nitrogen is absorbed, if you've got the very small pores that we call micropores, the molecular sieve type pores, then you get very high absorption at very low relative pressures. You see that with zeolites, you see that with carbon molecular sieves, although they also have higher level porosity. You see that with our polymers. So they really do behave phenomenologically like a molecular sieve. What does that mean? It means, and now we said we can turn them into membranes. They actually, we can use these as membranes to try to separate gases. They're particularly, this particular polymer became known because it beat the upper bound of performance for certain gas pairs that was born in 1991. In 2008, it was redrawn on the basis of polymers including ours. So here we've got a book. There's the structure of that polymer on the surface. This is actually a test module that was made by a Russian company to see how it would work. This is an organic molecular sieve. What we were actually trying to do is to find alternatives to things like zeolites, which were truly organic and therefore tailorable to interact effectively with organic materials. And this is shown here where we've got actually 3 different high free volume polymers. These aren't the only way of getting high free volume in a polymer. The most permeable polymer for many years was regarded as polytrimethylsilyl-propyne, which is a polyacetylene. There's another polyacetylene which is a very permeable polymer, even more permeable than PIM1. But what we have here is a dye. It's a blue dye in ethanol, and we could put a couple of different polyacetylenes in it, and particularly polytrimethylsilyl-propyne. It absorbs some of the blue dye. PIM1, which starts out yellow, it's absorbed all of the blue dye. It just pulls it all out of the ethanol. So it's changed colour and the solution is completely clear. It loves organic molecules. Now what does that mean? It means, for example, that you can build it into sensor devices. This is something that was published by an American company, not done here, where they built a sensor device for detecting very low levels of volatile organic compounds. And what they have is actually they have a polymer which is permeable and also actually acts as a mirror, and then a layer of what it says here is microporous material, which is actually our polymer, and then a half mirror which lets some light through. And because you've got a mirror and a half mirror, light, some will get through and reflect, some will reflect from the half mirror. You then get an interference effect which gives rise to a colour. And if this polymer absorbs something, that changes the refractive index. Also swells it a tiny bit. That then changes the interference colour. So you now have a very simple device which is in fact green when there's no volatile organic around, and when exposed to some organic compound, it turns a sort of reddish colour. So that just gives you an idea, because we've talked about glasses, rubbers, semi-crystalline materials, but actually we can design polymers that don't, well, this is a glassy polymer. It's a glassy polymer that can't become a rubber in the normal sense. We've never observed a glass transition. And that gives it a whole new range of properties. And that comes from actually applying some interesting chemistry and some interesting chemical intuition. There's a lot for chemists still to do. Next week, we're going to change the topic a little bit. one of the most important questions, because these are big molecules, how do we work out how big they are? And how do we cope with the fact that we always have a mixture? We're going to talk about that on Monday, next Monday, and in particular we're going to talk about how we can determine the molar mass and the molar mass distribution of a polymer. The next 2 weeks will really be focused around aspects of those questions.
Okay.